So I'm Or, and this is my Game Boy. So a couple of years ago, a good friend of mine, Noam, he asked me, what was the favorite thing that you hacked around? And I said, yeah, it's probably my Game Boy that I connected to my PC so I can trade Pokemon with myself. And today I'm going to tell you the story of this project that I did about 15 years ago in 2005. And at the time, there was already a big community of normal Game Boy and Game Boy Advance development. And there was a lot of homebrew and tools and everything, or many things were already in place. But for this talk today, I did the research and development from the beginning, from the ground up, so I can give you a full picture of what I've done at the time and what I've done this time to make it work again. So the GBA, or the Game Boy Advance, is a handheld video game console that was released by Nintendo in 2001, and it's a successor to the Game Boy and Game Boy Color lines. It has better CPU, this time an ARM processor, better video, larger screen, better sound, and advanced linking capabilities. So in short, the linking capabilities of the Game Boy Advance are twofold. One is called multipack gaming, and this is if every player has the same game, they put it inside all of the Game Boys, and you can transfer the game information and play multiplayer games. The other option is called single pack, or also multi-boot. And this allows you to have one game pack in the master Game Boy. It transfers some subset of the game information to the other Game Boys. They load it to their RAM and execute from there. And that's how you can play multiplayer games with only one game pack. 2002, at the end of 2002, the third generation Pokemon games came out, Pokemon Ruby and Sapphire. And as every Pokemon trainer knows, the goal of these games is twofold. One is to beat all the trainers on the map and become the league champion. And the second is to catch all Pokemon. While the first objective is quite easy and everyone can do it, the second one is much harder, because in every generation that there are two games like that, each game has a different subset of Pokemon. So if you want to catch all of them, you have to trade with friends that have both a physical Game Boy and the other version. So at the time, none of my friends had the other version or a physical Game Boy, so I did the only thing that made sense, and I turned to computers. So my idea in general was to take this setup and change one of these Game Boys and the human attached to it to my PC. So just to give you a little bit of background on what existed at the time, so the emulation scene was already was very strong at the time. An emulator is a machine that lets you, in general, play Game Boy games on your PC. So Visual Boy Advance is very known. No Cache GBA is another very good emulator. There were also many specifications documents, like GBA Tech and Cowbyte, and these give you an accurate description of the hardware and the software of the Game Boy that you can base your research or development on. And finally, there was the homebrew community, which included the toolchain, DevKit Pro, Xboo, and cards, which are different ways that you can load your own code to the Game Boy and run it. So I built upon these things when I did the original research. So a little word about emulation. So this is Visual Boy Advance, and it's running The Legend of Zelda, which is a very good game. Visual Boy Advance is one of the most well-known emulators at the time, and it's still a very good emulator. In order to build an emulator, such emulator, you need to have the description of the hardware. So for that, you can use the specification documents. The best one is probably GBA Tech, written by a guy named Martin Korth. He actually still updates it to this day. And this document contains very accurate description of how the Game Boy is built and what are the different memory regions that he has, the I/O registers, and we'll talk a little bit about it in a few minutes. So I set up a list of goals that I wanted to achieve in order to finally be able to finish my Pokédex. So the first one was to understand the physical layer and how data is transmitted between two Game Boys. The second is to reverse engineer the multi-boot protocol, which, like I said, this is the single pack gaming mode that will allow me to run my own testing code on the Game Boy so I can identify the sending procedures in software, and finally be able to implement link handling in the emulator itself, so that ultimately we can trade. So let's get a little bit into the details. So this is the link cable. It has two ends, one for the master Game Boy and one for the slave. The box in the middle is for connecting Game Boys number 3 and 4, so we'll ignore it at the moment. The link port itself, if you start to probe the pins, it's quite a simple cable. There are two common pins, which are the power and the ground, and there are 4 other data pins. So the SD and SC, serial data and sync, are used for transferring the data itself, and SO, serial output, and SI are used for serial input, are used for some kind of signaling between the Game Boys. So as you can see, the SO of one Game Boy is connected to the SI of the other, and this way you can chain a couple of Game Boys up to 4. And the SI of the first is connected to ground, and this is actually his way to know that this is the master. Okay, now I want to show you how it looks like in real life when you connect these two Game Boys and load a game from one to the other. So the game that we have is Yoshi's Island, which is also a very good game. I would like to turn. Okay, so this is a completely commercial demonstration. This is how the system should work, and this is what we'll try to achieve in the next few minutes ourselves. So one of these Game Boys, as you can see, it's very hard to see the screen because it's not backlit by itself. And this is probably the reason why I have glasses these days. So this Game Boy doesn't have a game pack inserted at all, and the other one has Yoshi's Island. And we can press the multiplayer. Okay, it already identified that it's connected to the other Game Boy. And it's transmitting data to be played on this one. I'll just say that the circuit that I have here, currently it's not connected at all. The cable is just cut in the middle. And this is the completely the way this system should work. So this is Mario running around. Okay, and this is the game. So the game data was loaded from the left Game Boy, the purple one, to the second Game Boy. Okay, we'll just attach these for the rest. Okay, excellent. Back to the presentation. Great. So now let's go a little bit down to the details. And if you put a logic analyzer on these 4 lines, this is what you're getting. This is a single sample of one transmission of data that is passed between the two Game Boys. For this, I used an Arduino logic analyzer, as I've used the Arduino a lot in this project, and we'll talk about the Arduino enough. So the 4 lines are as follows. The uppermost sync line signifies the duration of the entire transfer. The SD holds the bits that transfer between the master and the slave, and from the slave to the master. The protocol states that each Game Boy sends its data in its turn, and the turns change according to the SO line that is connected from the master to the next slave every time. The SI, as we've seen before, is always low for the master, and that's how it knows that it's the master. The number of bits that each Game Boy sends is 18, which is not a round number like 16, and the reason is that the first bit is the start bit and the last one is the stop bit. So in our case, the actual data that is transferred between the two Game Boys is 6202 and 7202 as the answer. To quickly summarize the layer 1 protocol, it's a fairly simple protocol, and if you connect the logic analyzer, you immediately see it. The master sets the beginning of the transmission, sends its data, including the start, data, and stop bits, sets the SO low to signal the slave that now it's his turn to send data. And in the next state, the slave sends its own data including all the bits, and sets the SO for the next Game Boy to start the transmission. The master waits for the timeout because it needs to know if there are more Game Boys connected in the chain. It doesn't know how many Game Boys there are, so it just counts the passing time. And if a timeout occurred, then the transmission is over. It says the SC high, and that's it. Now, one more thing about the transmission. The length of each bit is 8.7 microseconds, which gives us a baud rate of 115 to 100 bits per second. And the duration of the entire transfer is around 350 microseconds. Great. So now that we have a basic understanding or a good understanding of the layer 1 protocol, we can proceed to the multi-boot protocol itself. Now there are two ways that we can get the protocol. One is to sniff the transmissions that go between the two Game Boys and to see what is transferred, and the other is to reverse the BIOS or the games and to see what is the algorithm that is found within them. So for the sniffing task, we can use our Arduino sniffer, which is connected to the circuit in parallel. And using the Arduino runs at 16 megahertz, which should be enough for the sampling rate. It can give us like high enough accuracy for getting the individual bit. Notice though that we don't have any clock signal. So we have to keep the timing very accurate the moment the transmission starts. We can know it happens, and then we have to keep the timing accurate. And doing this using Arduino works very well. The Arduino has multiple GPIO pins which allow you to connect directly to the digital circuit of the Game Boy. It has built-in timers, and this mechanism works very well with the Arduino. And this is an example of what we get when we perform this sniffing. So it's connected to 3 parts. This is from the beginning of the transmission, the middle of the transmission, and the end of it. Right now we can see some things that are of interest, like things that seem like counters that going down or going up, but we won't put too much effort into this. We'll just use it when we start to reverse the code. So when we get to reversing, as I said before, GBA tech or these other specification documents are very helpful. Okay, in this example, we can see that they give the memory map of the Game Boy. We can see they say exactly, okay, the BIOS is loaded at address 0. The games or the ROM is loaded at address 8 million. We have an address of RAM, which is 3 million, etc., etc. And if we use this documentation, we can load all the data that we have into IDA very neatly in the right sections. Everything fits exactly. It makes the reversing much, much easier. Another very important part in the specification document is the I/O registers map. The I/O registers are the way of the Game Boy to give the software some ways to interact with the peripherals. So these are memory addresses that if the games try to write to these addresses, then something happens with the hardware. For example, they write something to the screen, or sound is produced, or communication is initiated. If they read, they can get the actual state of the keys, for example, which key is pressed, etc. So if we add this information also to our reversing, we can get exactly what's happening when the code tries to write or to read from a specific address. Okay, great. So let's read some assembly. So I put here a couple of examples from the reversing of the, in this case, the BIOS. So the BIOS is the code that runs when you turn on the Game Boy and there is no game inserted. Yeah? This is the logo that comes up. So one thing that I saw that was quite nice to see is that the BIOS is loaded at address 0 and starts to run from address 0, which is something that I haven't seen lately. Another thing is the software interrupt table. So this is a list of functions that the BIOS provides the ROM or the games that they can use. Turns out that one of these functions is a multi-boot function that performs the communication to load this code to the other Game Boy. Another part of the BIOS code is the code that handles the multi-boot transmission. How do we know that this is the right place? Because of the I/O registers. These are the registers that are responsible for the transmission. We can also see some familiar numbers like 73 that we've seen in the sniffing, or 63, 64. And if we combine the information that we got from sniffing and reversing, it makes it easier to understand what's the algorithm here. And the last example is the game code. This is Yoshi's Island. And here we can see the multiple handling that is done in the game itself. So again, we can see call to this software interrupt function that's in the BIOS, and we can see references to the relevant I/O registers, familiar numbers again. And the reversing of this is quite straightforward. There's not a lot of code going on, but it's as if a very good exercise. So this is, in short, the entire multi-boot protocol. So there are a couple of stages in it. The master Game Boy probes the slave to see if it's there. They send header. They ask for an encryption key. The encryption is pretty much storing the information with a byte or a couple of bytes, nothing more than that. And they really had very minimal security in mind. Then the main data is sent. The transfer is finished, and then both sides compute CRC, exchange it, make sure that the information is correct, and if it's correct, it is executed on the slave. Just if we go back to the dump or the sniffing that we saw earlier, then we can now understand what were the things that we're seeing. So at the beginning, we had the probing and the header that is sent to the Game Boy, to the slave. Then we have the encryption key and the main data. And finally, there is the checksum. The last transmission that we see is the checksum sent from the master to the slave and from the slave to the master. They match exactly, and the code is executed. Okay, great. So we have layer 1, and we have the multi-boot protocol. So what we would like to do now is to change the role of the Arduino from being a sniffer to being actually active in the circuit and be the device that communicates with the Game Boy. I would like to connect the Game Boy directly to the PC, but there is no interface at the moment that can do that. And we'll talk about this in a few minutes. The thing is that the Arduino needs to get the information from the PC and send it to the Game Boy in this special serialized format that it has that sends it 16 bits of information. So again, the Arduino is very good for this task. It's a very simple development board it has GPIOs that can interact directly with the Game Boy. It has these built-in timers, and it's very easy to use it specifically for this task. So its main purpose is to wait for 2 bytes that will come from the PC. It will transfer these bytes to the Game Boy, get the result, and send it back to the PC. That's all. And just as a small anecdote, this is the original circuit that I used for this. It's a circuit proposed by a guy named Miguel Ajo. It's based on microchip 16F84, which was also very fun to work with. And in order to work with it, you have to program it. So apparently programming it is not so trivial. You have to build like your own programmer for it or buy it. So at the time I was very in the mode of do it yourself, and everything like I did to do in my own. And this was the no parts peak programmer, in parentheses, almost no parts peak programmer. And when I was building it, then I came across some problems, and I didn't know. It was like my first time doing these electronics and all that. And I went to the forums of Microchip. At the time, I don't know if Stack Exchange exists or not, but it was definitely not as common as today. And I found some guy who helped me build this circuit and build like more circuit that I built after. And his name is Keith, and he helped me a lot, and we are actually in contact to this day. Great. So now we have the Arduino circuit that's connecting the PC to the Game Boy. And we know the multi-boot protocol, and we have everything in place. So now we can try to load our own code to the Game Boy in preparation for the next steps. Okay, so in this demonstration, what I have is a Game Boy with no game pack inserted. It's connected to the circuit that I have here. And I'm going to load code from my PC to the Game Boy. Now you might see that what I have here is not an Arduino, but rather a Raspberry Pi, and this will be very important in a few minutes. Okay, it jumps a little bit, but what we're seeing, I'm trying to load this code. The first two lines are the moment that it tries to see if the Game Boy is there or not. This is where he sends 6202. The header data is sent, though it doesn't look like that, so I'll run it again. Okay, for every demonstration I have a backup video, so don't worry too much about it, but we will try to make it work. Excellent. So the header was loaded correctly, and now the main data is sent. The problem was that I forgot to disconnect the other Game Boy, so okay, excellent. Yeah, so it seemed as if I loaded lots of code, which is true because the toolchain puts in lots of stuff, but this is what we got. Excellent. Oh. No. Okay, back to the presentation, please. Excellent. So now we have the multi-boot actually working, so we can load our own code to the Game Boy, execute it, and use it to whatever need that we have. So now let's go back to emulation. So this is Visual Boy Advance again. It's running Rayman 3, also a very good game. And this is where we want to put our code in. We want to integrate this circuit into the emulator to allow us to play these multiplayer games with the actual Game Boy. So an emulator is a system that allows one system, the host system, in our case a PC, to run another system, which is the Game Boy. So it has to somehow simulate the entire environment that the Game Boy expects to have, or that the Game Boy games expect to have, on the PC. And this is what Visual Boy Advance does. And it has a main loop that is the one that's responsible to simulate the entire action of the system, of the Game Boy. So in this loop, it has to simulate the CPU or the opcodes running and changing the internal state of the CPU. It has to simulate the accesses to the memory, either reads or writes. It has to take care of reads and writes to the I/O registers, which means that if the program writes to some register and expects something to happen, for example, something to appear on screen or to get the state of the currently pressed keys, then the emulator has to also simulate this. Timers is also something that is very important in an emulator, and in general, the emulator is responsible for keeping the timing of the entire system consistent. Okay, so it has to make the game think as if the time passes in the way it expects it to pass. After the emulator finishes the simulation or the emulation of what it does, it then produces the sound and the video to the player on the host system, on the PC, so you can get the screen back. So what we would like to do is to put some code in these parts that will make the link possible, the link with the real Game Boy possible. So one place that we need to add our functions is the handling of the I/O registers. So there are a couple of I/O registers that are important for the initiation of the communication and to check its status. So this is the first place that we will put our code. And the second one is the update function, which is the function that runs all the time and checks whether the transmission is over yet. And if it's over, then it updates the necessary registers or raises an interrupt or whatever happens actually in the hardware. So since we have the multi-boot protocol and we can run our own code on the Game Boy, we can now use it to better write the emulator, or to make it very accurate. So we can write custom, and this is a thing that I wrote for this time, not for the last time. We can write a custom testing software that will run on the Game Boy itself, and it will run on the emulator and allow us to compare what happens in the real system and in the emulator. And our goal is to make the emulator as close as possible to the real system. Okay, a good emulator does exactly that. So a couple of things that we can test is, for example, the register state, or how does the game sees the environment of the Game Boy while it performs the transmissions. Another thing that is very important is the timing, okay, because the timing takes some time. So if the game expects the timing to take 1 millisecond or something around this area, then it should take 1 millisecond. We don't want to cause it to think as if the transmission happened faster than it should, or slower. Okay, so we implemented everything in the emulator. We have our Arduino circuit. Everything looks good. We've tested it. Everything works fine. And now we can try some real games and see what's happening. So, lots of link errors. And now I think, okay, but everything seems okay. The hardware, the Arduino is okay. The data is transferred to the Game Boy correctly. We loaded lots of multi-boot code, and it works. No problem here. We've also tested the emulator, and it works. It looks as if the data is transferred correctly. So what is the problem? And now begins the story of the state that I was at 2 weeks ago, or 1 week and a half ago. As I was preparing for this conference, I took out like everything, and I worked for several weeks on the previous stages. And then I got to this point, and suddenly nothing works. Okay? And this is the main thing that I want to show here. So it turns out that the main problem is latency. And there are several links in this chain that cause latency. The Arduino is, in this case, to blame, because it uses the serial over USB interface, which adds like several delays. So one is the USB architecture itself, which is like this master-slave that uses polling, and it may add 1 millisecond of delay just for communication. Then there is the extra serial communication delays. And then there is some packaging, some buffering done by the operating system, which add several milliseconds of delay to the transfer, specifically to the beginning of the transfer. So we don't have a problem with throughputs, just with how long it takes the data to be sent to the Game Boy from the moment the game intended it to be sent. So this fails, and this causes the communication with the Game Boy to fail. And now an interesting thing is that at the time I used the parallel port, and the parallel port gave me direct GPIO access from the PC. Okay, and today we don't have this anymore. So what can we do? So with help of some very talented guys from my work, we went to search for other solutions. So we looked for different boards, maybe Teensy or M5 stack, in order to eliminate this delay. Actually, there was no much better solution. All of them somehow have to communicate with the PC, either over USB or over Ethernet, whatever. So there's no way to get rid of this. So instead, the idea that came up was to compile everything on a Raspberry Pi and run it on a Raspberry Pi. So the Raspberry Pi is much more powerful than Arduino. It has a 1.6 gigahertz processor. It's an ARM processor. It has those GPIO lines that give us, again, direct communication with the digital lines of the Game Boy, which is great. Compiling on the Raspberry Pi works very easily. It's very good. So we just adapted the Arduino code to it, implemented again everything that we did with the multi-boot protocol and the code that we have and the code that I've showed you earlier. We integrated the link code into the emulator on the Raspberry Pi, compiled it, and things got better. So the delay dropped to virtually non-existing. From the moment that the game writes to the I/O register that starts the transmission, the data is sent over to the Game Boy. Then we did a couple more of like these micro optimizations, which is a task set to dedicate a CPU core to the emulator itself, some improved timing, which means that we make sure that the timings are not too fast or too slow. Frame skipping and throttling are terms that used a lot in emulation, and it means that we can render only the second, third, fourth frame, etc. So we can not make the system too busy. Or throttling, which means to keep it running at a constant speed, which could be 100% or even faster. Okay, so now I have a disclaimer. The Raspberry Pi is almost strong enough to be able to run everything at the correct speed. So the trading, some games are tolerant for delays and some games are not. Pokemon are on the far end of the E-tolerant for delays. So I thought whether I want to try to trade live or not. So we will try to trade live 1 or 2 times. If it doesn't work, then we'll try another game. And if it doesn't, then I have a video. And if that doesn't work, then we'll go home disappointed. Okay, excellent. So this is my original copy of Pokemon Ruby. This is the task set on all the processes that we would like to remove from our CPU core. And this is our version, of Visual Boy Advance. The screen is small, so it will work faster. The thing with the battery, a small anecdote, is that the game pack itself has a built-in battery to keep the real-time clock working. And if it runs out, then you don't have any more events that are based on the time of the day or the day of the week. Okay, in the background you can see the communication. This is what the master sends, and this is what the slave sends back. This is like real time. This is what's happening between these two now. As you can see, the right one is slower, which sometimes is okay and sometimes not. And this is the link error. We'll try it one more time and then we'll change. Don't forget to breathe. Okay. So we'll try the other one because I do want. Okay, what we'll try now is Rayman, and here I will use the single pack mode to load a subset of the game to my Game Boy, so we can play between these two. Okay, great. So it did recognize the other Game Boy, and data is sent. And this is the actual game data that is now sent to the other one, and should allow us to play a multiplayer game. Okay, great. So I need a volunteer to play this game. No, I'm kidding, it's okay. I play with myself. This was the idea. Yeah, so these are exactly the way it means to work. It was meant to work with two actual Game Boys. So I'm very sorry for the Pokemon trade. It takes maybe like a couple of tries to make it work, but this is for the future. So can we go back to the slide? Okay, a number of small takeaways that I have on this project. At the time and looking back, I really liked this project because it gave me a very wide view of an embedded system. The Game Boy specifically, it's also very fun to work with, but it's also a very good example of an embedded system. It is complex enough, but still simple enough so you can understand every aspect of it. For example, here we can see the communication stack. So we got from the very low level, bit level, and you can use your logic analyzer and electronics and whatever you want to get this layer 1 protocol, and then you can go up the layers and find the layer 2 protocol, the multi-boot, and how the games intend to use the link features, and you get to see everything. You do a lot of development, so you do this low-level development, you do high-level development, you get to reverse engineer the games or the BIOS or whatever you want in this, and you can have a very, very wide view of it. It's also a very cool project, and what I liked this time around, that I found new problems that didn't occur the first time. So now these latencies, they are a new thing that didn't happen because then I had a parallel port. So another thing that you can take is that newer is not always better, that's for sure. And this time it had some new challenges which were fun to work on and still require some work to make it work perfectly. Great, thank you.